This is to review worksheet 2. This is to worksheet 2 of chapter 10, worksheet of Ochem, provided by class. Starting off with number 1, you have to draw all the resonance structures of, let's say, this molecule. How would we go about it? All possible resonance structures would look like, we can do fishhook arrow. This goes here. We get the following, and then this can combine like the following here. And you get following resonance. So I would suppose 3. This is part A. So get part B. If we had the following connected benzyl compound, resonance we could draw for this is this. So that we get the following, but also we could go down this route if we if from here actually we have done this, then we get another form of conjugated system. Followed by this, and so we get from here we get what seems like this, and that seems to be about 5. Let's check the answer key. The answer key shows 3, 4, 5, 2, 3. Yeah, this is correct. This is correct. We have to rank from most stable 1 to least stable, which is 6. Let's go about it. If we were to rank from least stable to most stable, it would be the following. The most stable would be, I would have to say, probably either the benzylic or the tertiary / allylic. I feel very tempted to say it's the benzylic, but this is the first one because it's allylic. And this one here is benzylic, so they're equivalent, what seems like, but they're actually not, because the one here is, I think, secondary, and this is tertiary. And tertiary allylic is much more stable. So followed by benzylic, we get least stable would be this phenolic. And then it would be followed by this tertiary, and then secondary, and then primary. So get the answer key. 524 163. This is right. this, say we went through. And then if we did chlorination under light, we would get, say, what would we get as the major products? What are the major products? Say if we did that, and if we did BR2 and heat. Well, BR2 we said is more endothermic, so it would favor likely this position. Chlorination under light is not so selective, so you'll get this plus this, and also this. Let's check our answers. Alright, yep, this is correct here, but we're missing one for chlorine. For here, it seems like we also get something. We also forgot this carbon. So, forgot this part. So then, if we did so, we should get that. Chlorination is not selective because it's exothermic, and it's not selective as bromination under radical conditions. Say for part B, say we had this molecule, we reacted under HBr and peroxide. What would happen? Well, if we had to predict the major products, we know under hydrobromination and radical conditions such as light or peroxide, we would get anti-Markov addition of the following. Reduction or something. So we would get anti-Markov. Oh, and to point above, seems like we get racemic here. Let's double check above. Ah, yes. We get racemic there. I see. Something looks off. No, wait, so why is the top one over here? Why should we have that there? Should not be the case. Okay, yeah, this here is racemic because this is a hydrogen. There should be a hydrogen. Yep. Looks like that was wrong the first time. We did not catch that. So we get two racemics. Is that correct? We get two racemics. We get two racemics. Two racemics. And yes. Like as shown. This seems now it's correct. That's right. No, this here is very bromination under radical conditions is very selective. We learned that. And now we shall address this. Under HBr, what would happen? Markovnikov, I believe. It would be Markovnikov carbocation formation, SN2. what will happen is we get BR like this. If that's the case, yep, it looks great. However, it's not rhythmic because we got two methyl groups. And so, yeah. I forgot something, folks. The above here is rhythmic because we got 4 different groups. Other than that, it's correct. Bottom here, this is also correct. Under C, say we got the cyclohexane. We reacted it under NBS and heat. What would happen? Looks like under NBS and heat we get allylic. Seems like we will get allylic bromination. However, be on the watch because we could go through a rearrangement. NBS allylic bromination can undergo a rearrangement of carbocations. Say this were the case, what would happen? We would say for example, there was like a hydrogen there. We could use radical reactions, promote this here. That's where we get, and so we'll also get a terminal allylic product. So that it looks like the following. I believe. However, is that it? Yes, that seems it. On to D. Seems like if we have the following. If we have this following, and let's say we go under molecular bromination and we reacted with light, what would happen? Seems like here we go theoretical bromination. Would we form more major products, or is selective not so selective? Oh, here we said it was very selective, so our major products would probably go with the available carbons, hydrogens. Forgot what the mechanism kind of looks like for this. I shall explore it soon. But let's say our products would look like this. Just because. Would we get BR here, maybe? This is my pure guess. If that's the case, that seems to be the only major product. Let's go look at C. C seems like, this is correct. However, forgot to mention this is rhythmic. And for D, for C, continue, this is rhythmic. Out of the two, which one is major and minor? It seems the answer says, the key says this is major. But why? I shall review this. So is it Zaitsev? Is it Zaitsev's? This is our first question of the worksheet 10. title will say worksheet 10 take 2 take 2. Alright, if that's the case, let's see. Is it Zaitsev's? Is it Zaitsev's? If it's Zaitsev's. Okay. Major, but why? So why is it major? Is it Zaitsev's? Yes, it is Zaitsev's. Seems like. Why is it more Zaitsev's? Listen, we should write that down. These are the reasons why we do review worksheets. Okay. Great class. There is. Sorry. 10. Take 2. April 16. Question 1. Why does allylic bromination products favor Zaitsev's product? And this raises, is NBS considered small enough what? Reagent, and is it relevant? And is it even relevant? That should be our question. Okay. And now to answer part, because remember an elimination Hoffman is when we do E2 elimination but we use much stronger or much sterically hindered bases. However, in this case we're looking at NBS, and we're looking at, not even sure if this is relevant. Well, continuing on, let's look at D. And D shows that. Oh, looks like we have it right. We have actually here. Seems like our answer is just this. We get racemic here. But note, nothing about the stereochemistry here changed. So we get a mixture of diastereomers. That seems to be the answer. Now, should we move on? Part E is this benzylic. Is this benzylic ring, and now that we look at this, say we reacted under NBS and light, what would happen? Allylic rearrangement can happen, remember? Yeah. So what would we get? We would get this benzylic product / alkene. We will just attach the bromide here, but also there's the alternative. If we do the alternative, we could get allylic bromination here. Don't forget, we can do rearrangement. If we have hydrogen here, let's say we can recombine, and the following, then maybe we could get, I think we would then be able to get BR like this. But is that it? would we be able to... This is a tricky problem, because say we were to keep on pushing those electrons, those darn electrons, we would get many possibilities. But that's only half the story, because this here can also undergo more rearrangement. I feel, and no, this is not C, this is an H. And if this were the case, I feel like we could go push it harder. Say we were like this, and we would get BR here. So let's do the count. We get 1, 2, 3, 4, 5. Do we get 5 products for E? Let's check. It seems we know this is wrong. What? What the heck? Why is this wrong? It's none of these. This is wrong. And this is wrong, and this is wrong. It's just these two. Okay, looks like we'll have to review mechanism. NVS mechanism. And answer, this is our second question. Why not carbocation rearrangement? Or sorry. Oh wait, we're not looking at carbocations. I think we're looking at only radicals. Radicals cannot undergo rearrangement. Or is the part can they? This is one heck of a problem. Sorry, this is not correct. Only one of this. This is not correct either. What the heck is? This is not correct. Alright, let's do the math, or let's do the reasoning again. So, if this were the case to be entering its mechanism, radical here, it would combine, bam. Then the rearranged product could be looking like the following. Then this would look like the following as well. That's our second product. It's this product and this product. Now let's use deductive reasoning. Why aren't the other possibilities possible? Alright, because we are not to look at hydrogen shift. It's not carbocation. It's a radical. That's why. There's only 2 possibilities. Now only one of these is actually major. Now the answer key I think it said was... Which one was it? The answer key says this was major. Why? Because this is conjugated. Conjugated. Now the question I think we should ask is, okay, so we know it's not a carbocation rearrangement. We just need to ask what is the mechanism of NBS. But also, we should address what makes conjugation more stable. Okay, that's number 2. So what are the resonance possibilities within NBS mechanism, and how do we classify conjugation stability? This shall be saved for later. Now, this is important. It's just this product and also this product. No more. That was a very messy problem. EF. Now that we look at problem F, let's look at the following. Say we have an alcohol, and it looks like the following. If this were the case, say we were to react until hydroboration under peroxide. In the second step, we use a strong base. What would happen? Now, thinking this through, this is part F. Thinking this through. If we were to start off with the first mechanism, we used hydroboration. If these were lone pairs, what would happen? The question we should ask is, would the alkene be the nucleophile or the alcohol? This is a good review question. Question is, would alcohol or alkene work as nucleophile in same compound? This is a good question. Would an alcohol or alkene attached to same compound either act as nucleophile? And explain with pKa? Maybe. We'll do that. But from what I remember, alcohol would probably do it because that's the lone pairs. My question is, because lone pairs? Question mark. Dump those electrons off. Would this be it? The hydronium would be a good leaving group. Makes sense now, makes sense. And so if this were the case, then we would get a very good leaving group. Reminds me of Artemis spacecraft when it's about to depart of the space Orion capsule. If this were the case, now then it would make sense to work this as the nucleophile. Oops. If this were to attack the leaving group position, this would now want to leave. If that were the case, how would this work? Ring closure. Carbocation would like to go probably in the... Wait a second, is this even right? I'm confused. What do we actually do from here? This is a hard problem. Matter of fact, now that I bring up bases, when does strong sodium hydride NaH, when does that even work? It seems to be the case that Let's look at the answer key. E, F, G. It looks like we have the right idea. Okay. Looks like we did something wrong completely. We were wrong. It does not start with the alcohol because we do not want to see that leave wrong. So our question now should modify to why is it not alcohol? Because matter of fact it's actually the alkene that functions as the attacking molecule, our nucleophile. If that were the case, then now everything falls into place. So this is wrong. Instead, what we should get is untouched alcohol and say we have this, and we'll get carbocation here, so this will be the BR position. Oh shoot, I completely forgot this is a radical mechanism. Okay, that changes up a story. Alright, I forgot radical mechanism. Oh shoot, what does this mean then? So the first question was why would alkene take precedence as nucleophile over alcohol when both are attached to the same compound? And explain with pKa. Maybe that's a good option. Okay, I'm gonna look at the answer key right now. It seems to be the case. No. Because peroxide, this will be anti-mark. I should have caught this on much earlier. My silly mistake. So this is our what's so-called intermediate step 1. Now what happens from here? I would say because Br is a good leaving group, are good options for nucleophile to be here. This will attack the leaving group and ring closure. It'll be 1, 2, 3, 4, 5 carbons total. So we keep the hexane the same, and it'll be 1, 2, 3, 4, 5, and then closed by the oxygen. However, because we sacrificed lone pairs for a single bond, it will be positive here. And what we can do is, I think we can use how do we deprotonate it? Maybe we can use the hydride to do this, maybe to form the final product of, or even if is this even a final product? I see. Okay. Right. Yeah, seems like we used this H. Seems we used hydride to maybe deprotonate proton. Interesting. S and 18. Well, there's that answer. There's that answer. Say we were to go on with part G. And we had the following molecule. The part G. Br2 radical halogenation, light. Selective, remember. Elimination, which we will use a bulky base ET elimination, especially, and then we will use epoxidation, followed by sodium, and I forgot what the fourth one represents. Does that represent? Maybe it's just hydration. I'm not even sure if it's hydration. That one we need a strong acid, not a strong base. Okay, shall we proceed? Let's do Br2 and light. Br2 and light is the first step. What happens? Selective bromination would result in tertiary attachment site, and so it would be Br. Now we're gonna do elimination, symmetrical, so don't even worry about the selectivity. This is what we get for 2. And for 3, what happens? Epoxidation. Epoxidation says we get the following epoxide, followed by 4 we will use this makes sense. Hydroxide will be the source, less substituted site, and I have a feeling it shall be, maybe it'll be opposite orientation. Maybe this will be OH. This will be, and obviously we'll do H2O to do acid quench. That's how we get the diol. Maybe this is our product. Let's check the answer. G. Okay, answer says that's very close. This would be either pointing, this would have to point down with the other hydroxide. But we get the enantiomer. Enantiomer meaning we get this as well. OH. OH. This is our other possibility. And that is correct. This is overall, seems, gist of it seems correct. Problem number 4 is a retrosynthesis problem. Say we had the starting or product. Say we had this product, we derived it from this. What would happen? Say we were to start off our synthesis with this, which is the only option we have. It seems like we will have to go through ozonolysis, but to get anywhere from here, we would probably have to do radical reaction. We could use probably bromination, radical reaction. We told you that this is selective, didn't we? If we said if this was selective, then this would result in tertiary bromide. Now, if you want to do it seems like we have how many carbons? 1, 2, 3, 4, 5, 6. We have enough carbons, nothing to worry about. Seems like we need to now use elimination. But if you want to use elimination, before we do that, we actually need a dihalide, but we can't add any more bromines in order to. So excess of bromine would not have given this. Instead, what we can do is sort of reverse process and then back to forward process. We could do elimination. For example, just use something simple as KO butoxide. Then we could turn this into, because if we were to tert butoxide, this is the debate I was making earlier. Would it be Hoffman or Zaitsev product? That would not matter. Hoffman, Zaitsev. It would not matter in this case because it's the only source of halide detachment or elimination. So in case we were to continuing use tert butoxide, say we were to use potassium butoxide. If that were the case, now we could do probably something like just normal halogenation. If that were the case, then we'll get the following. Probably stereochemistry would be anti-diol. And from here, what can we do? We learned because in terms if we saw this an aspect of HBr, then we could do double elimination. So Na sodium amide times 2 equivalents. What do we get? We get the following. Cyclic rings may not undergo. Are cyclic icons even possible? This seems oddly wrong. And why do we have extra? This would not even be possible. No, this is not possible. Okay, reverse thinking. What did we do? This just seems like a classic ozanolysis on alkene. We seem to skip all this step altogether, not even the halogenation. Let's go straight down to ozanolysis and water. Then maybe we'll get. So my question is ozanolysis of alkynes carboxylic acid? I should review this. Okay. It seems like that might be the product. Let's check the answer. Number 4, part 1. Yes, product. If this was product 1, this is correct. Now, let's see how we can generate product 2. How do we generate product 2? How do we generate product 2? Okay. Continuing on from our step over here, say we were to do something about it. That's a question I shall leave down for next time. And this is, let's just say it's very hard. It looks hard.